So much technology.
Yeah, and then you get a million warnings, right? Privacy.
Yeah.
Yeah. Okay, worked. But yeah, now we've automated it, so it's just clicking a button.
Nice.
And, yeah, that's good.
Wow, I didn't even know Zoom could do this. That's interesting. It's got built-in integrated streaming.
Sorry, say again?
I didn't even know that Zoom had integrated streaming inside.
Oh,
I think, right?
yeah. I think they do. I mean, at least the account that we have at UCL, because I'm sure there's like different levels. So we can stream on Twitch too. So
oh wow,
that's like the gamers platform, really, right?
Fancy.
So,
very cool.
Yeah, I mean, it makes it easier, and especially because I mean, right now you see there is a lot. It's not the same, obviously, but there's a lot more people that actually like, watch on YouTube either live or recording, and it's kind of nice to have a channel with all the videos there, and people watch it at their own pace. Maybe they slow down, speed up, or go back, skip some parts. I think it's I mean, I certainly enjoyed I probably watched more videos over the past 2 years than talks I would have attended at conferences, So
that's right.
That's
right, exactly. Oh, it's okay. Resume share. How do I? Okay.
Yeah. So we right. So yeah, I can see your screen, but it's not I don't think it's the first slide. I'm not sure.
I'm trying to resume share and it won't let me.
Oh.
Okay, so I'm gonna stop sharing and then restart the sharing again because it got stuck. Come on. Oh no. Oh, because 1 second.
Sure.
Of course, there's the inevitable. Now Zoom is giving me issues. Okay, so the trouble is I cannot make this full screen because if I do, then it treats it differently. And it doesn't stream as nicely. Okay, fine. We will live with that. Let me get back. Okay. Well, that's exciting. So, of course, fat finger mistakes. The sharing thing is right on top of the leave and the,
Oh, okay.
So, all right.
Yeah,
all the adventure aside. Yeah.
Okay, good.
Okay.
All right, great, thanks. So just a quick word of introduction for those of you who might not know who Ben is. I don't know, you've probably been living under the proverbial rock, right? So Ben Zhao is, thank you so much, first of all, for taking the time and giving the talk here and online, obviously. So Ben Zhao is a professor at University of Chicago. He was at UCSB before. He got his PhD from Berkeley. He has sort of many accolades. He's fellow of the SEM, got an NSF Career Award, was 35 under 35, and a number of many other awards. So overall, he's been working on and has been publishing and working in various areas of security and privacy, machine learning, networking, HCI, and so today he's going to talk about adversarial robustness via forensics in deep neural networks. Thanks so much, Ben. Without further ado, this virtual floor is yours.
Thanks very much, Emiliano. It's really great to be here, and thank you guys for the invite. So yeah, this is the beauty of Zoom, right? It makes sort of remote talks a little bit easier and simplify some of the longer range trips. So yes, I'm happy to be here to talk to everybody. I'm going to talk today a little bit about some of our recent work on adversarial forensics for neural networks. And just to preface it, I'm going to talk a little bit about some of our recent work in this general space of attacks and defenses, adversarial machine learning from the more security side and less of the core ML side, and talk about why sort of this switch to forensics is reasonable and sort of necessary. Okay. So, I mean, the obvious preamble on adversarial machine learning, I think everyone has some sense of what adversarial machine learning is. And obviously DNNs and deep learning has had a huge impact. So I'm not going to talk very much about, exactly how much impact there has been. It's just tremendous. So numerous applications, but we all know that it's vulnerable to different attacks. So whether it's adversarial examples or poisoning attacks or privacy attacks, like model extraction and, membership inference inversion. So at a very high level, there are multiple sort of communities, sub-communities within the large umbrella of adversarial machine learning. I'm primarily spending more of my time in sort of the security and privacy space, Oakland CCS, Usenix, that type of venues, whereas there are other large sort of sub-communities in the core ML area, but also, the application domains, for example. So, just as a sort of brief idea, we've had, if you will, a number of papers across different sub areas of adversarial machine learning. And particularly, I want to point out that the top two are adversarial perturbations and defenses, and also poisoning and backdoors. And so those are the two perhaps main sort of directions that adversarial machine learning has been focused on. And, most recently, I think the couple of green things are for papers that we have upcoming at UChicagocs in August. But I will in particular be talking about digital forensics for machine learning, focus on that, okay? But very briefly, I think, in case folks need a refresher, adversarial examples is this idea that for neural networks, given white box access, given full access to the model itself, and any sort of input, you can basically, normally you would classify some sort of benign classification, right? So here comes a normal stop sign. The DNN says, oh yes, this is a stop sign. But given access to the model itself, you can generate some sort of very simple adversarial noise that is quite subtle and difficult to actually notice with the visual, with the human eye, and in such a way that when added to the input, it will produce some misclassification, targeted misclassification, right? So you can make a panda look like some other animal, or lots of examples like that. So over the years, the attacks have gone smarter and smarter and smarter. Of course, here you can barely see the differences anyway, but they have gotten much more efficient and better at producing very, very subtle adversarial examples, literally completely invisible to the human eye, but harder and harder to detect even using other means, and also faster to generate. And all of them use basically the same rough idea of a gradient optimization, searching for sort of poorly trained sub areas in the classification manifold for a particular model once you have access to that model itself. So what I want to point out a little bit is that there has been this tremendous back and forth in terms of the research space between the defenses and the attacks. Okay, so if you just look back a few years, and of course this is forever for this research area, but really, we're still talking only about 8 years since the very, very first adversarial machine learning attack, adversarial example attack, FGSM. But basically what's happened since then has been that numerous defenses have been proposed, and every single time there has been a defense that has looked reasonable, a more powerful attack has come along and easily defeated it, right? In a fairly robust, fairly complete way. Okay, so again, I'm just sort of drawing out some examples of adversarial attacks papers that have really made a significant impact by showing that entire classes of defenses, for example, have been ineffective, and how they could be circumvented, right? And this has been going on for quite some time. There's even more recent papers that have been along these lines. I just haven't bothered trying to compress the timeline down to show everything. All right, so as far as I know, there is no known effective defense against adversarial examples right now, and accept effective meaning low cost and really high detection rate or avoidance rate. And the only thing that has been shown to really work, broadly speaking, in a general scenario, has been adversarial training, which by itself has really significant caveats. And so adversarial training takes a significant amount of time, and it also has the added downside of lowering benign classification accuracy. So these are all sort of not great things, and so we've been sort of locked in this struggle back and forth. So very briefly, I want to, this is not the point of the talk today, but I want to just give you an example of what it feels like a little bit to be in part of this cat and mouse kind of struggle. So we had a paper, this is back in 2020 at CCS, a year and a half ago already. And we had this sort of interesting experience really being inside of this cat and mouse game. So I want to just share that real quick. So very briefly, the CCS 2020 paper was just this idea that we wanted to do a defense that was significantly different in sort of approach compared to prior defenses. Prior defenses, really, you could sort of break it down to two different classes, right? So some basically said, there are these natural vulnerabilities in the classification manifold, and we're going to try to identify and remove them, right? So this is where adversarial training comes into play. This is where, randomized smoothing comes into play, right? Other defenses took a different approach where they would come and they would say, well, we're just going to make it more difficult for you to find those particular vulnerabilities, right? But most of these defenses sort of fell into one or the other camps. And so we want to try something different. We said, a lot of these defenses aren't quite working real well and they've been circumvented. So what if we do something different? And the thing that we came up with was this basically a honeypot approach, right? So this is not like trying to hide it or hide a vulnerability or to make it harder to find. In fact, it's the opposite. It's here's a generalized model. I mean, obviously this is not a real picture of a classification manifold, but you can imagine on the right, intuitively, that is what we're doing, which is that, there are some natural sort of holes or crevices in the classification surface. And what we're doing with this paper is basically saying, okay, we're going to create our own vulnerability that is so dominant and so pervasive that you can't help but find it. And because we are the ones who inserted it, we know when you use it to generate an attack, and we can, at inference time, actually detect such an attack. Okay, so the defender injects this sort of artificial vulnerability. In this case, you can actually use a backdoor attack to perform the what we call the trapdoor, and it basically creates such a significant impact in the classification surface that the attacker is using any sort of optimization method, whether it's something like as simple as FGSM or some of the more recent, more advanced techniques, Khalid Wagner, all sorts of different projected gradient descent methods. They will find our vulnerability really, really quickly. Okay, so and then at runtime, basically, when the attacker is trying to actually leverage that, you can actually detect this in real time, right? So it's pretty straightforward. You take some very small perturbation. I mean, it could be this little pixel pattern, or it could be like a little triangle in the corner, whatever. And basically, you train that into your own model, right? You're the defender. You're effectively trying to break your own model, but just doing so in a very deterministic way, such that you can recognize it later on. Okay, so I won't go through all the examples, but basically, the idea is that you're going to do this in such a way that the perturbation, that the trigger that you introduce into the system is the optimal solution for the attacker. That when they are optimizing for a small change that allows them to produce that misclassification, yours that you added will be the ideal, the smallest change. Okay. So, again, intuitively, this is what sort of this looks like. We sort of drew out this little intuitive figure, the idea being that, if you can see that here are all these natural, perhaps perturbation spaces, vulnerabilities that an attacker can already find. And basically what you're doing is you're injecting such a new dent, a large new dent into the space in such a way that it more or less dominates existing weaknesses, right? And so any optimization method that is reasonably good will find your trapdoor minimum instead of a natural existing normal minimum. Okay. All right. So, and then, at inference time, you basically look for this particular signature using a similarity function to any of the inputs that you get, right? And if the similarity is reasonably high, then you say, okay, this input is actually an attack, and so on and so forth. Okay. So this works pretty well. Again, this is not the point of the talk really, but this is highly effective. We showed it across lots of different attacks, lots of different models. It has all the things that you're looking for. It detects things really well without reducing model accuracy for benign inputs. Okay, great. Then we went through this ton of because this is sort of the style these days in the security community, which is, okay, providing defense, but you have to really think about adversarial adaptive attacks. So we created a bunch of sort of fairly detailed countermeasures of our own to try to attack our system. And there's there's nice behavior for the model defense that actually gets past all of them, right? And sometimes, you try to learn a surrogate model that doesn't have the trapdoor built in. It turns out you can't because they're so integrated. So when you steal a model, you actually steal the trapdoor along with it. Trying to crawl around this classification surface using really small learning rates doesn't quite work because the overhead is so high that before you detect one of these remnants, that it becomes computationally intractable. So lots of all these things, and we thought, okay, this is pretty decent. So what happens after we get the paper in? This is the fun sort of interaction, and I think many of you probably already know about Nicholas Carlini. Dr. Carlini is a well-known researcher in the space, and he's been at Google Brain for quite some time. So, and we know Nicholas for all the same reasons for some time now. So even before the camera ready, the minute the paper was sort of accepted and notified, Nicholas reached out and said, "Oh, this sounds really interesting. Can we get the source code?" I said, "Sure." And overnight he gave us a sort of an attack that basically said, "Well, this seems to break your defense." And we looked at it and said, "Oh, okay, well, this actually kind of works, but you're assuming a little bit more information than we assume, because we have some runtime random parameters that can help protect against defenses like this that are completely deterministic." And so it turns out, so we said, okay, here's a slightly stricter threat model. We want to have some runtime randomness that we can inject into the defense. And then 3 days later from Nicholas, he comes back with another attack that actually significantly weakens the defense, right? And so thankfully we had a few bullets left in our arsenal that we hadn't put into the paper yet. And so we add them, and it made it much more robust against Nicholas's second attack. But this was all, within the span of, a few days after just getting the paper in, right? And so this was great in a way that it was a really interesting sort of experience with, real-time revamping and sort of updating the defenses. So our camera-ready version actually had a whole section based on Nicholas's sort of contribution and his ideas on how to make this more robust, and it was a stronger paper. So we thought, okay, wow, that paper has been really gone through the gauntlet, and hopefully it'll be more robust. Not so much. So within a year, actually a year and a half, there were 2 papers that sort of came out with, the nearly explicit goal of attacking this particular trapdoor defense. And you can actually see the CCS paper literally has trapdoor in the title. So it was specifically designed to attack this particular defense. And Nicholas and his collaborators later on wrote a paper at iClear this year, which basically has a sort of more general attack based on his ideas for how to attack trapdoors, right? So what I'm trying to get across here is that trying to give people a sense of just how fast this cat and mouse cycle is, right? It's you do a tremendous amount of work to provide a perhaps what you think is a robust defense, and then very quickly the cycle turns, and then voila, you end up with a significantly weakened, if not broken, defense. All right. So one takeaway out of this is that if you want to actually do a defense, under reasonably strong threat models, it's really, really hard. Okay. There's a similar kind of story in backdoor attacks. Again, this is not the point of the talk today, but this is just one of our experiences from recent history. This was actually back in less than 12 months ago. This was last year at CDPR. But this was us on one hand, and again, I don't want to go through all the details, but backdoors are the other side of sort of the poison attack space. Okay, and the idea here is that you are introducing a deterministic trigger where once a classification input has that particular trigger, then the model is going to misclassify, right? So this is a very deterministic corruption of the model itself. And the way that you are going to, the attacker is going to make this happen is by poisoning the training data pipeline. Okay, so if this happens, then for example, any of my students here with some pair of sunglasses can all of a sudden be labeled as me by virtue of this particular trigger that is well recognized by the corrupted model. Okay, so in the CVPR paper, it was interesting. It was a little bit different because there had been a number of defenses that were built in the space that looked promising. And what we wanted to do was we wanted to sort of better understand if they would actually withstand real world attacks. And, so here are some number of defenses and, lots of attacks that were still coming out. It did seem like for a minute, a minute in research terms, it did seem like for a minute that defenses had the upper hand, right? But one of the things that was a really gaping hole was the sense that all these attacks were based on digital triggers. Okay, so what does that mean? That means basically, that meant that all the things that you're looking for to activate your corrupted model were, little tiny little pixel patterns that never actually occur in real life, right? So, for example, in facial recognition, you don't expect people to walk around with like a digital sort of some remnant of a small triangle pixels on their face, right? You would have to actually corrupt the video stream in real time to make that happen. So that's a very difficult thing. But instead, we thought, well, what would happen if, for example, we trained in backdoors that had a physical trigger like sunglasses, right? So in short, what we were able to do was to show that if you train an attack with physical objects as a trigger, then everything fails. All the defenses fail. And again, I won't go into details. You can look at the paper, but there's all very intuitive explanations for why the defenses fail. They make very strong assumptions about the triggers that actually don't hold up in real life. Okay, so the whole point of this is that in the backdoor space, again, the sort of the cat and mouse cycle turns around, and this time it's us in part taking the side of the attacker and showing that a lot of defenses actually fail to provide robustness against more realistic physical triggers. Okay, so if you step back for a minute, right, and think about sort of what does this mean, and this is sort of a thought process that I think a number of folks at my lab were undergoing after the recent experiences between the trapdoor paper and also the CVPR paper. And there was this sense that, are we stuck? Because it looked like that the community was really more or less in the cycle of defense, broken defense, defense, broken defense, right? There was not a clear sense that we were actually making things better and making things harder for the attacker, right? So it did seem like a perfect defense just seemed impossibly difficult. There's always a stronger, more powerful attack. And again, not like some of these attacks that were being proposed were some were incremental and some of them were, expanding the threat model, but there's generally speaking, always stronger, more powerful attacks within the bounds of the same attack model that come along and break the defense, right? And there seemed to be just some sort of built-in asymmetry. Attacks tend to be easier than defenses. For one thing, defenses had the burden of needing to be future-proof. right? Whereas attack papers, you tend to write them, it's like, okay, well, if you break everything right now, there's no assumption about requiring your attack to withstand all future defenses, right? That's not necessary. It's just necessary for it to break things right now, which is seemingly a little bit of an unfair advantage built in, right? But that is the world that we live in. And so when we think back to, okay, well, if you are actually trying to improve robustness for these models, what do we do? Because continued participation in this cat and mouse game seems a bit counterproductive, right? You can always do better. You can always build another defense that looks stronger, looks more robust, but you expect that within some short amount of time, the attackers will come along and basically break it. And so does that actually help real systems? Does that actually increase robustness? Of course, there are things that we're learning in the cycle, right? And new directions that are being explored, but is it an actual takeaway for people who are practitioners who actually want some mechanism that helps them? That's not going to be broken in the next 12 months. And so one of the possibilities that comes out of this is that I had this hypothesis that perhaps one of the things that's going on is that we are, in a sense, stuck because the threat model that we have right now is fairly limiting, right? And I'll explain what that means in a second. But in order for us to make better progress, perhaps what we need to do is actually expand the threat model, not just sort of stay within the same threat model and just keep grinding defenses and attacks and defenses and attacks. So what do I mean by the threat model? Well, let me take one example of this, and at the very end, I'll mention some others. But one example of this is to realize that the current view of adversarial attack and defense is very binary, right? So, for example, if you take a DNN defense, and you have a simple attack or a reasonable known attack comes along and it gets blocked, and you're like, okay, great, the defense works. And then you get a stronger attacker who comes along and perhaps circumvents the defense and breaks it. And all of a sudden the response is, well, that defense was crap, so let's trash it. And now we're back to square one, right? So it's very binary in the sense that you either have something that works perfectly, or once compromised with some sort of weakness, that's it. That defense is really useless now. But that's not how real world systems work, right? Real world systems are not perfect when they are deployed and remain perfect. In fact, this is an example of, I think, a Boston Dynamics robot. Reinforcement learning is a thing. Learning from deployed systems is a thing. And generally speaking, the idea is, well, defenses are not perfect. In a more traditional security domain, for example, lots of network defenses go out there, and they're just part of the solution. And that attackers, if they want to, will eventually win, given sufficient cost, given sufficient computation time. But in fact, there is such a thing as what you do after a compromise, because compromises do actually happen in the real world. So we sort of try to draw a parallel between what's going on inside the ML space and what actually happens traditionally in the security domain in the real world, and think, well, what is it? How do we expand this view that we have right now in adversarial machine learning to be more reflective of real systems? And one such answer, right, is to go beyond the sense of like, once the attacker has won any sort of battle, that's it, your model goes away. But instead looks at what happens after the attacker has some reasonable success, right? And this is where sort of digital forensics comes in. So what is digital forensics in a more traditional domain? Right, the high level idea is, okay, some sort of attack has happened. Some sort of an attacker has successfully circumvented your system. Okay, you gather some piece of forensic evidence. Let's say a single example of something that can get past your system. Right, but then you can go back and use that evidence to trace back to the attacker, get their identity, whether it's IP addresses, whether it's user accounts, and actually seal them off, right? So potentially block an IP address and block an account. It's not, forever, of course, attackers can always come back, etc. But at least you have a weapon to deal with the attackers after a successful attack, right? And really, there's a couple benefits of forensics here. One, it's interesting because it allows you to identify where the breach happened, how the attacker was able to circumvent your system this time. You can trace it back to that weakness, that hole in your system. You can plug it, patch it, whatever you want to call it. But also, more importantly, the successful use of forensics provides a deterrent against future attacks, right? Because now attackers know that, okay, yes, I can potentially break your defense and circumvent it and successfully attack your system. But I have to understand that even if I do, I will probably leave a trail of some sort that can be then used to identify me after the fact, right? So yes, I can win, but the win comes with the cost of potentially revealing some amount of information which will be used against me, and perhaps in the sort of most ideal case, law enforcement or whatever serious repercussions actually happen. But at minimum, there will be things like the hole that you came through will be identified and patched, right? So let's talk about what this actually looks like for machine learning. So this is much of this comes from a upcoming paper I used in security in August this year, right? So again, just to remind folks, right, the idea behind a data poisoning attack. So let me preface this by saying that digital forensics for machine learning, the first piece and probably the easiest piece is for data poisoning attacks, right? And we have some other work looking at adversarial examples, but that's still in pipeline. So I'm going to really talk about and focus on the poison attack side today. So poison attacks, if you remember, is the idea that there's some corruption in their training data pipeline, right? So a model is being trained on top of this model and on top of this training data, and some portion of the training data itself has been corrupted and is controlled by the attacker in such a way that your model is going to be corrupted when you train on this training data, okay? Now at deployment time, the idea is that, okay, if someone has gotten through your system, they've gone ahead and successfully poisoned your model, then they're presumably going to make use of it, okay? So the idea of forensics is to do something after the attack has happened. So let's say that the attacker makes this happen, gives you an input, and it basically says, oops, it's going to misclassify as something different. Maybe this stop sign becomes a speed limit thing. But you notice this, right? So perhaps there's some cost already damage involved for someone who has now gone ahead and attacked your system and compromised it. Maybe there's some downstream, evidence or damage that's taken place. That's unfortunate, but such as the nature of forensics, that you're really attacking the sort of studying the attacker after the attack, right? But the assumption that we have is that after this attack, there's some little bit of misclassification evidence. And in the case of poisoning attacks, misclassification evidence is quite small. All you really need is a single sample, a single input that is shown to cause misclassification from your model. And that's it, right? So that's your sort of trail of the attacker and nothing else. A single input that triggers the misclassification behavior in your model, and that will be sufficient. Okay. And then using that misclassification evidence, of course, the goal is to go back and say, I want to basically understand where the malicious data was that came and corrupted our model, that was responsible for encoding the misclassification behavior inside our model. And of course, hopefully that will lead us a little bit closer to the attacker, right? In practice, for example, you can imagine that if we're able to do this, what this means is that if there is a poison attack, that then you can basically go back and say, after the attack, you can say, well, how did the poison happen? Was it a server breach, right? Because potentially I can say, if I have decent logging, if I have decent data tracking on my on my training data pipeline, then I'll be able to identify, once I see that this particular portion is the malicious data, I can say, well, I have logs that show that this data was, introduced into the training data on a particular date on my server, right? So that will basically point me to some sort of server breach. Perhaps that training data, that malicious training data came via a mislabeling process, right? Maybe one of my data annotation services was bought off or infiltrated by an attacker and intentionally fed me bad data. But again, knowing which samples are malicious allows me to go back and to identify those annotators as untrustworthy so that I can prune them from my data training pipeline. Okay, so I hope I've explained this well, that once you have the forensic traceback for a poisoning attack, it means that you can understand where the attack came from and you can effectively close the door, right? So we're not really going to talk about like how that final closing the door happens. It really varies quite a bit depending on how the data, poison data corrupted came in through the pipeline. But you can imagine that that can be quite effective once you know which data samples are actually responsible for this particular attack. Okay, so how do we actually do this? Of course, is the more interesting question. And the high level idea is that we're going to basically cluster the training data and we're going to test with unlearning, right? So what that means more specifically is that we are going to take training data and effectively iteratively prune it using clustering techniques to test to see which subsets of the training data are innocent. And we want to remove the innocent parties. Okay, so basically, iteratively, every single test step, what we're doing is we're saying, okay, here's all the training data that we have, divide it into 2 clusters, and train using only one subset, one portion of the training data. Does the trained model still produce the misclassification behavior that we have before, that we know is our attack? We can test that very easily. Why? Because we have that forensic example, that single misclassification example. So that is our litmus test, and you can basically train subsets of the model using subsets of the training data. And if something preserves the misclassification behavior, then you know that the training data you just pruned away is innocent. You can ignore it, and then you can just focus on the chunk or the cluster of training data that is responsible that you're looking at right now, and then just iterate. Okay, eventually you're going to iterate until you cannot prune any more clusters, and that ends up being the responsible training data set. Okay, and you're going to cluster the training data based on how the data impacts model parameters, and the details of this in the paper, but it's fairly straightforward. So let me show you the intuitive example of what happens. So in iteration 1, for example, let's say that you've got all the blue squares and the red triangles. That's your entirety of your training set. But you're going to perform some sort of clustering algorithm based on sort of proximity, if you will, in the feature space of the training data. And after one iteration, what you can see here is I basically made a clustering division and partitioning right across the middle of the training data. And once after I tested it, I see that training a model using the left side of that partition produces a model that does not show that misclassification behavior. Okay, therefore, I can assume that that portion is benign, and I'm going to throw it away. And now what I have left after the pruning is a smaller portion of the training data that still includes all the poison training samples. So now you can imagine iterating, okay, and then you can do this again, and this time hopefully your cluster, this is obviously a very simple example, but with this second iteration, you're dividing between a cluster of benign, cluster of poison training data, and again, once you do the pruning, you'll get a version of it that you'll be able to basically prune and identify the benign subset of the training data. Okay, and what you end up with then is this little cluster of poison data. Okay, so why does this work, right? To understand why this works, it helps to understand why poison attacks work. Poison attacks work because you are basically training a specific rule about a misbehavior into the model. You're forcing it to learn something that is unusual. So what that means is that, for example, you had to supply with sufficient corrupted data to say that, anything with this tiny little pixel pattern, for example, is going to be a speed limit. All right. So in order for you to do that, you actually have to have a cluster of poison data that is so significantly different from the rest of the benign data that it actually alters the trajectory of your classification behavior. Okay, so this is sort of an intuition of why this thing works. This is a 2D sort of PCA visualization of the projected training data for a bunch of different combinations. So BadNet, Trojan are the two main training models. Physical backdoors is our CVPR paper that broke all the defenses. And as far as the applications go, we've got CFAR10, VGG facial recognition, and the Winger one is also facial recognition. But basically what you see is that you see all the poison data happens to be really far away from the benign training data. And this is really the core idea here, that the poison data has to be far away in the feature space from the benign data if you want a smaller portion of the poison data to have an outsized effect, right? If it's reasonably close to the benign training data, the effect will be minimal and you won't actually get the poison behavior that you're trying to get. So for poison attacks to actually be successful, this sort of distance is in many cases, or in all cases, necessary. Okay, and so this is the intuition behind why this works, because that big gap between benign and poison data is ideally what your clustering algorithm is going to pick up and what your pruning is going to leverage. Okay, so very quickly, lots of different, the usual sort of evaluations, lots of backdoor attacks, lots of different classification tasks. And we're really looking at precision and recall, right? This is pretty straightforward idea. We're trying to identify all the poison data and none of the benign data. So poison basically says, precision basically says, of the data that you identify, did you make any mistakes? And then recall, of course, says, did you miss any poison data? Did you get it all? Okay. And if you look at the results, are really quite high, right? Everything is generally speaking above 99%. And again, it's because of that intuitive, natural separation that is necessary between poison and benign data. If you don't have that separation, it's very difficult to get a poison attack to actually work. Okay, so the false positive rate is also quite low. I will just point out that, for the weakest result, if you will, the 97% result, only occurs in the recall side. So what does that mean? That means that you have some poison data that is not terribly effective at pushing the poison. And so because of that, it's actually being sort of left out in the identification defense, okay? But that's sort of, if there is a small little deviation from the ideal, that's where it's happening. But what you do identify is almost always 99% correct, okay? More interestingly, we actually go beyond sort of what we call traditional dirty label poison attacks. We actually look at clean label attacks. And I don't want to spend time explaining clean label poison attacks, but it's a very interesting attack where the attacker does not control their own label, but they can control their own inputs, right? So they can shift their inputs using their own benign label, but shift it in the feature space to cause misclassification around someone else. Okay, so I won't explain the details of that attack, but I will just say that we actually tested across quite a few of the most recent and strong clean label attacks. And we actually showed that clean label attacks were also able to detect them really, really effectively. Again, the precision is always near 99%. And the thing that is, relatively speaking, a little bit weaker is recall. So sometimes when the poison isn't super effective, it can scatter around the feature space, and sometimes they can elude detection. All right, so I know I'm probably running out of time a little bit here, so I want to just briefly talk about countermeasures. Of course, countermeasures are a thing, and so the details are in the paper, but we tried a bunch of different things intuitively to try to circumvent the forensics methodologies. So how do you get past this? Well, ideally what you do is you can try to say, okay, so all the way on the left is the benign sort of vanilla attack. This is where the poison data is sufficiently far away from the benign training data, right? In A. Now B is basically saying, okay, can we push the poison closer to the benign data in such a way that they won't be identified as their own cluster? Turns out when you do that, basically the poison attack fails. Okay, well, what if we inject more helper data, more benign data that sort of extends a bridge to the poison data so that, again, they form a cluster that is difficult to identify? Well, it turns out that actually doesn't work. That gets detected as well. can you bifurcate the poison data? Can you create multiple overlapping poison attacks? There's a bunch of these that we sort of built into the paper. And it turns out that it's still either or, that either the poison attack itself fails because you've manipulated the poison data so much that it's no longer able to imprint that strong misclassification behavior into the model, or it's just not enough separation, or it's just not too much separation still between the poison data and the benign data. Okay, so this is still coming back to that intuition that I talked about earlier, which is poison data needs, in order for it to be effective, it still needs separation in the feature space from the benign data. And that is the reason that this still works. Okay, so I'm going to try to wrap up here now and sum things up. And so what I'm trying to hopefully get across in this talk is, I think we're plateauing in the adversarial machine learning space with current attacks and defenses. A lot of the papers that I do see in the submission pipeline are sort of stalled around the same general space, right? Smaller changes, tweaks to different attacks and potential defenses, but we're sort of plateauing a little bit in what we can do. And so I think one of the things that we can, as a community, as an area, sort of grow is to change and evolve our threat model to be more realistic, to be more impactful to real running systems. And what does that mean? So that means any number of things, right? So the example that I've been talking about today is the Unix paper is really talking about expanding our definition of attack prevention and robustness, right? So yes, the attacker can win. That does not mean that you throw everything out and you go bankrupt. It just means that you have post-attack systems like forensics that can come back and add additional value. There are other ways of evolving threat models. You can think about like time varying things. What happens when you no longer are fixated on a single snapshot? You can think about broader definitions of attack success and failure. What happens when partial compromises can happen instead of a single binary, misclassification or not? Okay, so anyway, I will probably end there and see if folks have any questions. Thanks.
Great, thank you, Ben. Really great presentation. Yeah, I think we can maybe stop the recording and live stream, but I think I gave host permission to Lorenzo, so I can no longer do it.